SwayamPrabha. Digital India. Educated India.
Okay, so we'll continue our discussion where we stopped the previous class. So we developed a stress diagram from beta plot. So we have to convert this diagram to this diagram, and so you know that how to convert beta to alpha. Okay, and finally we get OA, OB, OC, OD and OE in terms of stress diagram. Okay, this is nothing but our yield locus, and we can mention OA as alpha is equal to 1 and OB as alpha is equal to half and OC as alpha is equal to 0 and OD as alpha is equal to minus 1, and this is the last one where alpha is equal to minus infinity we say, and then correspondingly there is beta values. So now we will see some details about each one. So here you can see in the equibiaxial stretching alpha is equal to beta is equal to 1. That is basically your if you see the previous one, it is OA. This is OA path. So if you look into it, since alpha is equal to beta is equal to 1, so we are going to develop some relationships which will be useful for our discussion. And you will see that sigma bar is equal to square root of sigma 1 square minus sigma 1 sigma 2 plus sigma 2 square, and this is as per von Mises yield function. And here you will say that if you put alpha is equal to 1, you will see sigma bar is equal to sigma 1, which is nothing but sigma 2. Okay, so your effective stress is nothing but the principal stresses. And when you go to next one, that is your OB. So, okay, this is OB. Okay, so here you will see that beta is equal to 0 and alpha is equal to half. Right, alpha is equal to half here. Okay, so alpha is equal to half. So here you will see that if you put alpha is equal to half here, so you will get sigma 1 equals 2 by square root of 3 into sigma bar, which is nothing but 1.15 times sigma bar, and sigma 2 is equal to half into sigma 1 because alpha is equal to 1 by 2. Right. So for a given flow stress, here you will see sigma 1 is greater in this process than any other. We will see that. Okay, here sigma 1, which is principal stresses, is 1.15 times your sigma bar, 1.15 times sigma bar. Okay, and if you go to the next one, uniaxial tension, where beta is equal to minus alpha is equal to 0, if I put alpha is equal to 0, sigma bar is equal to sigma 1. Okay, and then you will see that your sigma 2 is 0, sigma 1 will be nothing but sigma bar is nothing but sigma f, which is nothing but your flow stress. Okay, so you can see that both are equal here, sigma bar and sigma 1 and sigma f all are equal, but here if you see that sigma 1 is 1.15 times sigma bar, and this occurs in tensile test. If you go to the next one, that is drawing, where alpha is equal to minus half and beta is equal to minus 1, if you put alpha is equal to minus half here, you will get the membrane stresses as sigma 1 is nothing but 0.58 times sigma bar, which is just half of sigma bar. Okay, if you go to the previous one, okay, you will see that your sigma 1 is equal to 1.15 times sigma bar. Here sigma 1 is equal to sigma bar, and here you will say sigma 1 is equal to 0.5 times sigma bar and sigma 2 is equal to minus of 0.58 times sigma bar. What does that mean? That means if you compare this with the previous one, the magnitude of stresses to cause deformation are at a minimum in this process. Okay, in drawing, okay, when you follow a deformation path where alpha is equal to minus 1, beta is equal to minus 1, then you will have a magnitude of stresses which is going to be minimum. That is, in magnitude they are only 58%. That means 0.58, I am saying 58% of stress required to yield a similar element in simple tension. So if you go to uniaxial tension, okay, you are deforming the material and you want to yield it, so then you need to go to sigma 1 is equal to sigma f, but at the same time same material, same element, you are going to deform it in drawing, then it will be only 58% of that. Okay, so it is going to be a minimum in this process, whereas you will see that it's going to be greater in this case. In plane strain, it's going to be greater. Why? It is because 1.15 times sigma bar. So here it is 1.15 times, here it is 1 time, and here it is only half of that, 0.58 times. Okay. So in uniaxial compression, you will see that since sigma 1 is 0, if you substitute here, you will get sigma 2 will be equal to on the negative side, which will be your minus sigma f, and this is going to create a wrinkling on the flange of the sheet. And we have seen this example uniaxial compression at the edge of the flange region. So you will see that you are going to have wrinkling because of this. Okay. So this 5 parts, OA, OB, OC, okay, and then you have OD, and then you have OE. Okay, all are coming from this particular one, OA, OB, OC, OD, OE, and you will see that if you are deforming in this particular stress path where alpha is equal to -1, you can deform the material to reach yielding, okay, pretty easily, and it is about 58% of that what is required in uniaxial tension. That is what we have shown in this particular comparison, in this one and this one. Okay, so just to complete the last section of this particular, then we will go for a couple of problems. You will see that principal tractions or tension. Principal traction or tension. Okay, so tension is nothing but force per unit length transmitted in the sheet. Okay, or you can also say it is traction. Traction means just pulling. Okay, so T1 is nothing but sigma 1 into T, and T2 is nothing but sigma into T. So sigma 2 by sigma 1 into sigma 1 into T, you can say, which is nothing but your T2, and you will see that this is going to be your T1, okay. So, and this is nothing but your alpha. So, T2 is nothing but alpha into T1. So, T2 is nothing but sigma 2 into T, or it is nothing but alpha into T1. So, sigma 2 by sigma 1, sigma 2 by sigma 1 is nothing but alpha. Similarly, we can say T2 by T1 also as alpha. Both are one and the same. So, now you can see that like sigma 1 versus sigma 2, you have a yield locus, okay. We can also have tension locus, T1 versus T2, okay. So, this can be obtained from sigma 1, and this can be obtained from sigma 2, okay. And you will see that there is an yield locus, okay. Similarly, there will be one tension locus which is given here, okay. There will be a tension locus which is given. This is similar to what we have seen in yield locus, okay. So, there is something called sigma bar we discussed, okay, and sigma bar will lead to sigma bar is nothing but effective stress, right. So, effective stress will lead to effective tension, which is given by T bar, which is nothing but sigma bar into T. So, you can directly write that as square root of 1 minus alpha plus alpha square into T2, okay. So, sigma bar we wrote it as square root of 1 minus alpha plus alpha square into your sigma 1, right. So, this will be T1. Okay, this has to be T1, I think. Okay, what is this one? Into sigma 1, no? So, this will be T1. Okay, so if you know this T bar, then you can get this yield locus, right. So, we are not going to use it, rather we are going to use only the yield locus. This will be helpful for us when you evaluate the tensions, and now we are going to introduce something which will be useful for our next chapter. Okay, so what is that? Suppose in this equation T1 is equal to sigma 1 into T, okay. T1 is equal to sigma 1 into T. In this equation, okay, if you use the material law sigma bar is equal to K epsilon bar power n, then what will happen? You can say that this sigma 1 is nothing but sigma bar square divided by square root of 1 minus alpha plus alpha square, isn't it? So, sigma bar is K epsilon bar power n. So, this you can combine as 1, and T is nothing but T naught exponential minus of 1 plus beta into epsilon 1. So, if you combine this, you will get this particular equation. So, T1 is nothing but sigma 1 into T, where sigma 1 is nothing but sigma bar divided by square root of 1 minus alpha plus alpha square, and T is nothing but T naught exponential minus of 1 plus beta into epsilon 1. This we have developed in the previous section itself. Okay. So, now you will see that this equation is a function of some material properties and your beta and alpha and your epsilon 1 strain, right. K and N, you know, strength coefficient and strain hardening exponent. T naught is the initial thickness, beta is your strain ratio, alpha is the stress ratio, and finally the only variable is epsilon 1, and for epsilon 1 you can get epsilon bar also, because by knowing beta you can get epsilon 2, epsilon 1 and 2 can be obtained. So, 3 can be obtained. From this you can get epsilon bar. Finally, you will see that T1 as a function of T1 as a function of epsilon 1 and T2 as a function of epsilon 1 can be drawn, and here it is given. Okay. So, from this we can get T1 and T2, where T1 T2 are related by T2 is nothing but T1 into alpha. Okay. So, from this equation you can fetch any values for this, and you can get T1 versus T2 here, T1, okay, or T2 versus epsilon 1 you will get. So, and you will see that for those cases when you have beta greater than minus 1, beta greater than minus 1 means, that means these fellows, beta greater than minus 1 means this side. Okay. So, for those cases where you have thinning, for those cases where you have thinning, you will get maximum load. Okay. You will get maximum load, and after that you will see that maximum load is going to decrease, or tension is going to decrease. Okay. So, T1 is obtained and T2 can be obtained by knowing alpha. Right. So, if you want to find this maximum tension, okay, so then you can get it by taking dt1 by d epsilon 1 as 0, and if you solve it, you will get epsilon 1 star will be equal to n by 1 plus beta, and this value will be this one from 0 to this. Okay. So, you can solve it and find out, okay, or you can do it graphically also, but you can choose k, n, t naught, beta, epsilon, alpha, you can choose, and if you change epsilon 1 as a variable, you will get T1 and T2 in this way, and only for beta greater than minus 1 you will get such situation, this kind of situation. If it is less than minus 1, then it will never come down, okay, because beta is not going to be greater than minus 1, then thinning will not happen, okay, then you will not see this maximum tension. Okay. So, only if you have beta greater than minus 1 you will get this particular situation, and the maximum tension can be obtained when you have epsilon 1 star. We are going to call this as star because it is going to tell the maximum value. Epsilon 1 star is equal to n by 1 plus beta, where n is your strain-hardening exponent and b is your strain ratio, beta is your strain ratio. Okay. So, if you know epsilon 1 star, you can get epsilon 2 star as 2 star as beta into epsilon 1 star, considering proportional process, the beta is not going to change, let us say. So, now for uniaxial tension, suppose beta is equal to minus half, okay, beta is equal to minus half, if you put epsilon 1 star is equal to 2n, and for plane strain if beta is equal to 0, you will get epsilon 1 star is equal to n. What does that mean? That means if you deform a material in uniaxial tension, okay, so the material is going to fail at a strain of 2 times of strain hardening exponent. At the same time, if you deform the material, same material, when you have plane strain process, epsilon 1 star will be equal to n. Okay. So, what does that mean? That means the material can extend to a larger value of epsilon 1 when you deform the material in uniaxial tension as compared to plane strain. So, in plane strain the material can fail, or material can reach this maximum value, which is a indication of something like instability, okay, then that will be reached early in plane strain process, okay, at epsilon 1 star is equal to n. So, if n is equal to, let us say 0.22, so epsilon 1 star will be equal to your 0.22 into 2, that is 0.44 in case of uniaxial, but the same time it is plane strain, means it is 0.22 only. Okay. So, in that case the material is going to reach failure or instability in plane strain much early as compared to uniaxial. Okay. This is going to lead to a good next chapter, some theories we are going to develop for instability. This will be a basis for this. So, where once this star indicates that the material will be in some sort of instability or a maximum load is reached, maximum tension is reached. Okay. So, we will stop this theory part with this. We will solve 2 problems in this now, okay, which are going to be useful for us. Okay. So, first problem is, okay, a small circle of 5 mm diameter is printed on the surface of undeformed low carbon steel sheet with thickness of 0.8 mm. So, T naught is nothing but 0.8 mm. So, we will take T naught as 0.8 mm and initial diameter of the circle, let us say D naught as 5 mm. Let us pick up this way, and it is a plane stress proportional process, and it is a plane stress proportional process. So, after deformation, the major dimensions are given, minor dimensions are given. What are they basically? It is, let us say D major as you can call it as 6.1 mm and D minor as 4.8 mm. Okay, and effective stress strain relationship is a standard one. So, we need to get alpha here, and then T1 and T2, and then you can get effective strain. So, as we discussed in the previous chapter. So now the point here is once the dimensions are given, we have to get principal strains, right? So epsilon 1 is, you can directly get ln of 6.1 divided by 5, okay, that will be about 0.199, and then epsilon 2 can be obtained ln of 4.8 divided by 5, which is going to be negative value. If you know these two, you can get epsilon 3 as minus of epsilon 1 plus 2, which will be this, okay. So now we need to get alpha. So for that we need to get beta, because strains are known. From beta you can get alpha. So what is beta? Epsilon 2 by epsilon 1. So 0.041 minus 0.041 divided by 0.199, it will be minus 0.21, and from here you can get alpha as 0.324. Okay. So alpha has been found out. So now alpha has been found out, is fine. Then we need to get effective strain. So that is also another question. So it is understood that it is von Mises equation. So square root of 4 by 3 into 1 plus beta square into epsilon 1. So you substitute beta, this particular beta value here, you will get epsilon bar as 0.21. And the tensions T1 and T2 can be obtained. We just now derived it. Okay, T1 and T2 we just now derived, isn't it? So T1 is this. If you know T1, T2 can be obtained by alpha into T1. So T1 is nothing but this value, k epsilon bar power n divided by 1 minus alpha plus alpha square into T naught exponential of minus 1 plus beta into epsilon 1. So all values are known to us. So this is your k, right, and this is your n. So all are given. So 600 into 0.21 power 0.22 divided by square root of 1 minus alpha 0.324 plus 0.324 square into T naught is 0.8 exponential minus of 1. Then beta is nothing but, where is beta? Minus 0.21 into 0.199. If you calculate T1, it's going to be 329.3, about 329 kilonewton per meter. Okay. So you have to check the units. Please check the units. It has to be consistently used. Please check it. And T2 you can obtain by alpha into T1. What is alpha? It's already known to us, 0.324 into T1. It will be just 1/3 of this. So this will be your 106.7 kilonewton per meter. Okay. So this is one easy problem. Okay. So these all are known to us from the previous chapter. Epsilon to get epsilon 1, 2, 3, beta, and then alpha, epsilon bar we already done. Only difference is now we calculated, we derived an equation for T1 and we derived an equation for T2, and T1 and T2 are nothing but major tension, minor tension. Okay. So that is the only extension in this chapter, and you know how to get it. Similar problem. Okay. So suppose you are doing deep drawing. Okay. So this cup deep drawing, you know, the strains in the center of the base A. So this point is, let us say A, halfway up the cup wall. This is your cup wall B. Okay, and in the middle of the flange, that is in C. Okay, these three values are given as 0.015, 0.015, 0.050, 0.15 minus 0.1. These all values are given. Okay, this is nothing but strains, that is epsilon 1 versus epsilon 2. Okay, epsilon 1 and epsilon 2 are given for these three locations A, B and C. This A is here, B is somewhere in the middle, and C is somewhere in the middle here. Okay. The strain hardening of the material is negligible, so that effective stress is constant. Okay. So here they are saying sigma bar as a constant value. Constant value means what? Okay, there is no hardening in the material. So which means that your flow stress is going to remain constant at 300 megapascal, which is easy for us to calculate. Initial thickness is given as 0.5. So T naught is given. Okay, so what you need to get is basically at each point, this A, B, C, you have to get the new thickness and major tension, that is T1. New thickness T and major tension T1. That's all you need to get. So now how do we go ahead? So like now strains are given. So directly we start getting one by one what is the requirement we have. So you need to get T, that's a new thickness, right? So new thickness depends on the original thickness by T is equal to T naught exponential epsilon 3, correct? So now here you need to get epsilon 3 because T naught is known to you, T naught is already given. Okay, epsilon 3 has to be found out. So epsilon 3 is nothing but minus of 1 plus beta into epsilon 1, right? So for this beta should be known, for this epsilon 1 also should be known, which is already given for each points. So how do you get beta now? Beta is nothing but 0.015 divided by this 0.015, then 0 divided by 0.05 which is 0, minus 0.1 divided by 0.15 which is minus 0.667. If you put beta is equal to 1, 0, minus 0.667, in this you can get alpha. You know that for beta is equal to 1, alpha is equal to 1. For 0 it is half, this is known. Okay, this is balanced biaxial stretching and this is plane strain. Okay, so and here this is going to be a variable. Okay, it is 0.251. Okay, so it is a plane strain. Plane strain is half, isn't it? So plane strain is half. We said plane strain is 0, beta 0 and alpha is half. Beta 0 and alpha is half. Beta 0, alpha is half. That has been obtained. So now everything is known. Okay, so all the values are known here. Epsilon 1 is already given in the value 0.015. So minus of 1 plus beta is 1. You substitute everything here. You will get this value and this value for the different parts. A location, B location and C location. Right. So now our question is, there is only one variable, that is epsilon 3 here, that you can substitute in this. You will get a new thickness 0.485, 0.456, 0.456. Right. 476. So there is a less decrement in balanced biaxial. You will see more change in thickness in case of these two. Now you want to get T1. What do you need to do? Your T1 is nothing but sigma 1 into T. So T has been found out already. You need to get sigma 1. Sigma 1 is nothing but sigma bar divided by square root of 1 minus alpha plus alpha square. That can be found out. Right. So sigma bar is nothing but already given 300 megapascal. You have to just substitute as it is, because it is not going to be a variable. Divided by square root of 1 minus alpha plus alpha square. You can substitute alpha value and you will get 300, 346 and 262. Right. So you can see that sigma bar and sigma 1 are equal, isn't it, for balanced biaxial stretching. No? So that is what we have seen in the previous one. You can see that sigma 1, sigma bar are equal, isn't it? So that is what we got here in this problem as well. So which means it is good. Okay. So then if sigma 1 is known to you, sigma 1 into T will give you T1, that is major tension. T is already known. Okay. This is about half of each. 300 into 0.485, 340 0.476, 262 into 0.476, you will get these three values. Okay. So now by knowing T1 and T2, you can get not only the tensions corresponding to the principal stresses, but also at which stage of deformation you will get maximum tension, which is equivalent to some instability that is going to start. Now that can be obtained when you put epsilon 1 star is equal to your n by 1 plus beta. Right. So basically in this chapter we are discussing about how to find your strains at different locations of the sheet, and then some concept called strain signature we introduced, that is through strain diagram. Then we introduced how to interpret strain diagram, some important features we understood, then how to convert that into stress diagram, and then some important features of this 5 different alphas and betas we understood, and at the end we introduced major tension, minor tension, how to get T1 and T2 from sigma 1, sigma 2 has been found out, and some problems we solved just now, 2 problems, 2 examples. Okay. So this a small circle means it is given in one location, right. Similarly, you can imagine a sheet of 200 mm by 200 mm dimension. In all that location you have so many such circles. Okay. And in each circle you will have so many variables inside. Each location will have epsilon 1, 2 and 3 will be varying. Each location will have its own beta alpha, then epsilon bar will come and tension T1 and T2 will change accordingly. Okay. And this example is the best one to represent that. So different locations A, B and C, you will see that A is deforming in this fashion, B is deforming in this fashion and C is deforming in this fashion. Okay. And your alpha, beta, thickness, strain, sigma 1, sigma 2, everything is going to change as per the location and strains that we get. So we stop here. So in the next class we will start the new chapter.